Should I go ahead and share?
Ma'am, actually, Chandan will be introduced about you. Then after that, you can share your.
Slide. Yeah. So good evening, everybody. So this is my great pleasure to introduce Dr. Judy Jha. The talk is related to the phase transformation of nanoscale systems using in situ TEM, transmission electron microscope. So Judy Jha is the Carroll and Nobles Malamud Associate Professor in the Department of Mechanical Engineering and Material Science at Yale University. And she received, including the Gorde Betty More Synthesis Investigator Award in the year of 2019 and the NSF Career Award in 2018 and the Canadian Institute for Advanced Research as Israeli Global Scholar for Quantum Materials Award in 2017 and Yale Arthur Greer Memorial Award in 2016. Her research focuses on synthesis and transport measurements of topological nanomaterials and two-dimensional transition metal dichalcogenides and in situ TEM studies of phase transformation of nanomaterials and potential applications of these systems in quantum computing and energy. So I would like to request Dr. Judy Jha to start your session, and we would like to welcome you, ma'am.
All right. Thank you for the invitation. I'm looking forward to sharing our research. I'm going to go ahead and start sharing my screen slides. So this will stop other screen sharing. There you go. Let's see. Okay, so this looks good. Yeah.
Yes, that's fine.
Thank you. Can somebody remind me when there's 5-minute time? I would appreciate that if somebody can just shout and say, I have only 5 minutes. Okay. So thank you again for the organizers for inviting me to share some of the research from my group. As said in the introduction, I'd like to tell you a little bit about how we can study phase transformations of nanoscale systems using in situ TEM. So in my group, actually, we have 3 research thrusts. 2 classes of materials that I study are topological materials, but in nanostructures, and a lot of 2D materials. And subset of the 2D materials that I study are topological. Many of these topological and 2D materials have lots of different crystal phases. And with those different crystal phases, you have different electronic properties. So we use TEM and apply stimuli inside TEM to initiate the transformations and study how the transformations happen at the nanoscale. So just going back to the basics, I think all material scientists, the foundation of material science is structure property relations. And even if your material is made up of same element, depending on the crystal structure, the material is quite different. This is a well-known example. Diamond and graphite both are made with carbon. However, they couldn't be more different from each other. Diamond is hard, it's transparent, it's electrically insulating, and graphite absorbs all the light because it's electrically conducting and it's very soft. And this different property comes from the fact that the crystalline structure, how the carbon atoms are connected to each other, are very different. Now, one of the fundamental crystal transformation is that of crystallization. So crystallization is going from the disordered amorphous state to the crystalline state. So here you can see in this cartoon picture, these black and white circle atoms are randomly connected, and then you cannot identify the smallest unit cell, which you can repeat. You can go through crystallization event, and then now you're in the ordered state. So already by 1930s, researchers conjecture that this has to be the case. So crystallization is useful in our daily lives. And one example I'm going to start the talk with is actually phase change memory applications. PCM is a commercially now available technology. We can buy memory chips based on PCM. The well-known component is germanium, antimony, and tellurium. In short, we call it GST. And this GST, chalcogenide, can be in glass state, amorphous state, or you can easily switch it back to crystalline state. And this can be done with heating electrical pulses. And in the amorphous state, the resistance is high. And in crystalline state, the resistance is low. And using high and low voltage pulses, you can switch back between amorphous and crystalline state rather quickly and have high and low resistance states. So that forms the basis of your memory, 1 and 0. And PCM is considered one of the technologies that can perhaps fill the gap between our memory, which we can these days go hundreds of gigabytes, and hard disk, right? So storage, we now have terabytes, no problem, very cheap, but memory is still very expensive, and we're still limited in several tens of gigabytes. So eventually, we want to go to universal memory class where we don't have any of these distinctions. But before we go into that stage, right now, we're working on making storage class memory. And PCM is one of the memory technology that can perhaps fit all the specifications for the storage class memory. So working with IBM, so IBM has a site that's about 1.5 hours away from Yale. We looked at their next generation of PCM devices. So the current PCM device has a thin film of GSD. So GSD is the active component that does the phase change. And they have a bottom electrode as a plug, so that as you are flowing current, it locally heats near the bottom electrode. So now you have a partial crystallization, the event that happens. This is the commercially available current cell. And IBM has now been working on this confined cell where the GST, the active component, is no longer a thin film, but it's a pillar shape. And then there's this secret sauce of metallic surfactant layer that they've created, which is to help make the device run longer. So now that the device structure has completely changed and a lot of material processing conditions has also then completely changed, it makes sense to try to look at these devices inside TM, initiate the phase change between the amorphous and crystalline state, and correlate that to the device characteristics. So here, we look at the wafer, and then we use focused ion beam to lift out a slab. And here you can see a row of devices. Here is this one particular device in red dotted box that we're interested in. The rest of the devices, we cut it intentionally to make sure that there's no crosstalk between the devices. And now here's a zoom in image of this particular device. So this pillar that you see in this TM image is basically equivalent to this pillar in the schematic. So to operate this device, we're using a reset pulse. The reset pulse is going to make it into an amorphous high resistance state. So we're using a reset pulse of about 40 nanoseconds. And for the set pulse, so now that's going to crystallize the PCM. We're using a longer time durations to give enough time for it to crystallize. And also the voltage is actually slightly lower than reset. So let me play this movie right now. The resistance is 44 kilo ohm, and you can see that the intensity is rather uniform. And as we now pulse it, you can see that there are regions that are dark. The regions that are dark are the crystalline regions. The dark contrast is coming from diffraction contrast inside TM. And you can see that as we cycle between the reset and set pulses, the resistance becomes high and low. One thing to note is that the actual resistance values, when the device is inside the wafer, is much high and much low. So the contrast between the high and low resistance values are much larger in the wafer. But however, for in situ TM, we actually had to do focused ion beam milling. So that's why the device is actually not in the native state, but much damaged. Hence, the actual resistance values are different from the wafer values. But nonetheless, the key is that we're able to operate this device inside TEM. We're able to measure the device characteristics and correlate that to the actual phase transformation that happens. So immediately, what's clear is that the entire pillar does not crystallize. In fact, we see two distinct states. So here is a snapshot of two examples of amorphous state and then the crystalline state. Here is a number of cycles that we were able to run inside the TEM. We ran about over 150 cycles, and then the red dots are the reset, the high resistance state. The black is the low resistance state. And what you see is that there are two distinct crystalline states. One is the one that's shown here, where about 70% of the volume of the pillar is crystallized. And the other state is where there is a middle part that's a bit crystalline, and then the bottom part that's crystalline, separated by a little bit of an amorphous region. So you can see that since where my mouse is, this is less fractional volume that is crystallized, correspondingly, the resistance is actually different. So here, converting all of these data points in terms of resistance values versus the fraction of crystallinity, you see that here is the amorphous state, the high resistance state, and here are two different crystalline states, okay? So in situ TEM is indeed powerful to correlate the structure property relationships of nanoscale systems. One thing we also found is void formation, and the field has already known that the void formation is the leading cause for the device failure. So here you see there is a bright circle, and this bright circle indicates an empty pocket. Okay, so material has flowed up, leaving an empty space in between. Unlike the conventional cell, because this new device architecture is symmetric, we can actually reverse the current direction. So as you reverse the current direction, the material that flowed up can flow down and fill the void. So here you see the empty pocket is disappeared. This is reversible process. So here we can do this reversibly a number of times. And you can see that the resistance values correspond with the void formation. So when you have a void, it's air basically, and then that's quite resistive, so that the resistance is high. When you fill the void, then the resistance comes down. The physical explanation for the void formation is electromigration of antimony. So here is a device at the beginning. You can see that the antimony and tellurium is sort of throughout the entire nanopillar. And then we reverse the current direction and apply a voltage pulse. And then the amplitude of the voltage is a little bit high. And then with a single voltage pulse, you can see that the antimony, which was a little bit more concentrated near the bottom of the bottom electrode, has moved up all the way to the top electrode. While for tellurium, tellurium is still more or less distributed throughout the entire pillar. So it's the electromigration of antimony that is responsible for forming these voids. And the new information we've added to the community is that a single voltage pulse is enough to initiate this process. Another good thing about having a symmetric pillar is the fact that we can try to self-heal the device. So here was a failed device. The fib preparation went wrong. There was a little bit of a crack at the side of the pillar, and the pillar was half empty. So normally this will be an open device and you can't do much, but because the device is symmetric, we can reverse the current flow and then gradually fill the material. And then eventually this device then is operable. So here, this device becomes operable. So knowing this, we suggested to IBM that rather than using a single polarity for the reset and set voltage, meaning, let's say, always positive voltages, if you always use positive voltages, antimony will always flow in the same direction. It would make sense to reverse the polarity and then operate the device in a bipolar fashion. Perhaps if you use positive voltage for reset, use a negative voltage for the set. And what that will do is that the antimony will flow up in a reset pulse, but perhaps now come down in the set. So over time, the antimony will still be centered somewhat around the center of the pillar. Now, so this is an example of how crystallization is incredibly useful for our daily lives in the context of memory device. But if you take a step back and ask ourselves, what do we teach undergraduate students about crystallization? We teach fairly rudimentary concepts, right? We teach them classical homogeneous nucleation, where we say there is a Gibbs free energy that we have to care about. And when you nucleate, the surface is created, and then that surface is a positive energy term. However, at a certain critical size, the surface energy term is balanced by the volume energy term. And then once you overcome this nucleation barrier, then it's a downhill for the free energy. And that you're going to now, you nucleate a critical nucleus and they grow. But in reality, nucleation and crystallization is actually much more complex than just the classical homogeneous nucleation. There are many different pathways that the materials can take from either ions or atoms to the final crystalline state. It could be multiple droplets that are either polycrystalline or amorphous. Even in the amorphous, the density of these amorphous phases could be different. You could first form nanocrystals, and then they attach to each other in an oriented fashion. And all of these multiple pathways also means that the energy landscape is not a smooth function of the radius of the nucleus, where you have an R squared and R cubed term that is balancing each other. But it could be that you have many different metastable local minima, and that depending on how deep these local minima may be, it can be fairly stable in normal conditions. So how do we then understand nucleation and crystallization better? So for that, I work with my colleague at Yale. So here, this is Professor Jan Schurz, who's really well known in metallic glass field, and he fabricates at large scale these nanoscale metallic glasses. So here's an example of platinum-based metallic glass. So metallic glass meaning it's a metal, but in an amorphous glass state. And he can control the diameter of these glasses down to tens of nanometers. This is a great system to study crystallization because the bonds are simple metallic bonds. There are no directional bonds. The crystallization kinetic is slow, so we can try to catch the crystallization kinetics just using a regular TEM. And yet, the chemistry is quite complex, so this system has 4 elements. Therefore, we could study how the chemical compositions would affect the crystallization dynamics. So here is then a phase diagram of this platinum-based metallic glass. From the glass, at 230 is the glass transition point. If you heat it a little bit, it'll crystallize because, again, glass is a metastable phase. And at 400, it melts. And these are the bulk values. Here is the example of these nanoscale metallic glass. So we're ramping up the temperature from room temperature to 900 degrees Celsius. The movies I'm about to show you are sped up. So it tells you right now it's 170 C. The ramp rate is the same. So this is about 50 nanometer diameter. This is about 20 nanometers, and this is about 5 nanometers. When it crystallizes, the intensity will pick up. So you can see when these nanowires crystallize. They crystallize at different times, which means that they crystallize at different temperature. So immediately we know that there's nanoscale effects on the dynamics of crystallization. So we can repeat the same experiments as a function of the diameter of the nanorod. So here, going from about 300 nanometer wide nanorod down to about 15 to 20, we measure the onset of crystallization temperature. So you see the crystallization temperature initially decreases, and then this sort of agrees with our general understanding of heterogeneous nucleation. That the nucleation barrier is lower for heterogeneous nucleus, you're creating more surface for smaller rods, thus the crystallization temperature decreases. What was unexpected was this sudden increase of the crystallization temperature when the nanorod was below 30 nanometers. So what is happening? We did a number of experiments to try to explain how this happens, and at the end, the hypothesis we have is that when you have a small rod, the number of nuclei that you have in it is decreasing, and that the increase in the onset temperature is due to lack of nuclei in the system. Okay, so this actually affects the processing conditions for these nanorods. So let's think about time temperature transformation diagram, TTT diagram. So here's a temperature, here's a time. So at high temperature, things are liquid. And then if you quench the liquid really fast, then you reach glass state. If you quench it slowly, you have a crystalline state. And then the crystalline state has this nose shape right here as a function of time. So you can imagine at the nanoscale, you can vary the heating rate and then see when the critical heating rate will be as a function of the size of the nanorod. So here in the experiment, we can imagine heating it really quickly. And then perhaps we don't see any crystallization event, and maybe I'll then put it as a circle. So here is about 170 nanometer diameter rod at 3000 degree per Celsius ramping rate. If we heat it slowly, we should be able to see the crystallization event and then eventual melting. And then I'll denote it with a triangle. At the critical heating rate, we'll do experiments multiple times to make sure that that is the critical heating rate. So we repeat this as a function of the nanorod, and here is then a filled diagram. So this purple region indicates the critical heating range as a function of the diameter of that metallic glass nanorods. This data matches with the crystallization temperature data because the rate is sort of in a simple way, you can think of it as a 1 over the temperature. And you see that the shape then matches very well. This was for the critical heating rate. You could also repeat the same thing for the critical cooling rate. In this case, we shoot up the temperature to 900 degrees and stay there for less than 5 seconds. And then now we cool it at varying cooling degrees. So again, we see that the critical cooling rate is diameter dependent, size dependent. And then the overall behavior is the same as the critical heating rate. Let me just plot now critical heating rates and critical cooling rate. And when we do that, we see that a critical heating rate is about 1 or 2 orders of magnitude higher. And that's already, people know that that's the case. And the reason is because the maximum nucleation rate, it happens at a lower temperature than the maximum growth rate. So what does that mean? What that means is that when you're heating, as you heat, you're going to nucleate a lot of nuclei. And as you continuously heat, these nuclei will grow. However, when you're cooling, you first heat the maximum growth rate, but there's not many nuclei to grow. And then as you continue to cool, now you nucleate many nuclei, but your growth rate is low. So that's why the critical heating rate is usually high. The new finding from our work, in situ TM work, is the fact that at very small nanorods, the critical heating and cooling rate starts to overlap, and no longer there's a difference in the two rates. And then this actually agrees with this still supports our hypothesis that for very small rods, there's lack of nuclei. So if there's no nuclei, then it does not matter what your temperature processing conditions or history was like, because effectively you can imagine that you've eliminated this nucleation curve. And in fact, that we sort of demonstrated that it must be a single nucleus, because we can crystallize this multi-component metal into a single crystalline phase. So here is a small nanorod where when we heated it, you can see in the diffraction that this is a single crystalline phase. And then when we do chemical mapping, at least for copper and nickel, they're homogeneously distributed in this single crystalline phase, which should not happen for bulk. For bulk metallic glass that is platinum-based like this, you have binary phases that are thermodynamically stable, so that you have phase separations between those. And indeed, for larger rods, that's what we see. So here, For this rod that is much larger than this, it's in a polycrystalline phase from the diffraction, and also you have a copper and nickel-rich phases. Okay, so far we looked at nucleation part, but not the growth part. So the last example I want to show you is the growth part. So here, what we're doing is that we go to the growth temperature as quickly as possible, either from the liquid side or from the glass side, and we stay at this temperature. Now, if you do not consider the structure of the glass and only think about diffusion limited growth, then what this says is that irrespective of how the temperature has reached the growth temperature, the growth rate should be the same, as long as it's at the same temperature, because the diffusivity is only a function of temperature. However, what we found is that when you are heating up from the room temperature to the growth temperature, the growth rate is much faster. In fact, it's about 20 times faster. So this is the same nanorod that we recycle, and you can see that when you're coming from liquid to the crystalline temperature, the growth rate is much smaller. So this naive picture of it's only diffusion limited, the structure of the glass does not matter is wrong. So try to understand this better, we did an atomically resolved crystallization experiment. So here is just a snapshot. This is about 23 nanometer wide nanorod, right at 360 degrees Celsius. It's small enough so that we have a single crystalline grain that is growing upwards. So here is the boundary right here. And here is just a movie of this zoom in place. So you can see it's a layer by layer growth. So you can see the crystalline planes showing up, and then the crystalline planes are moving upwards, progressing upwards. So we can directly measure the rate of growth rate, by tracking how the boundary between the amorphous phase and the crystalline phase move up with time. And what you see is that this time-resolved growth rate is not constant, but rather it fluctuates. So this is interesting, and this reflects the fact that the glass state of metal has many different local structures, and that these local structures actually affect the dynamics of the growth. To save time, let me just say that what we think is happening is a lot of subcritical nuclei that is baked into the glass system, which is not thermodynamically stable and will not form critical nuclei, actually are coupled to growth. So in the PCM field, we know that the subcritical nuclei can enhance the rate of nucleation. But what we're now saying is that these subcritical nuclei not only enhance the rate of nucleation, but they can also enhance the growth rate. And since we have many of these subcritical nuclei baked into the glass state of our metallic glass, that's why the growth rate is a function of, it fluctuates, because as the growth front is meeting these subcritical nuclei, it enhances the growth rate. Thermodynamically, we learned that the subcritical nuclei is not stable. It should be fluctuating in and out of glass state or liquid state very quickly. So how is it that it can involve in growth process? Because growth takes in a much longer time. So I can at least show you that we have evidence of formation of a small nuclei that can survive for tens of seconds at an elevated temperature. So this nucleus formed, rotated around, and eventually dissolved back into the glass state. The surprising thing is that it survived for about 9 seconds at this 340 degrees Celsius, long enough to participate in growth. So to summarize, phase transformation at the nanoscale deviate greatly from macroscopic results. And in situ TM is a powerful approach to study these phase transformations. And then I gave you 2 examples. One was the phase change memory, and then the second was the nanoscale metallic glasses. I think my current interest is looking at the phase transformations in condensed matter systems, particularly topological materials. So in the remaining time, I don't know how much time I have because I don't have a clock in this room. Let me tell you about tin telluride, which is a system my group has been studying for a long time. This is a topological crystalline insulator. So it has many different topological surface states on the surfaces of these tin telluride. So my group makes it into nanostructures. And then the central goal is to induce superconductivity in these nanowires forms. And then that's because we think that this can be a materials basis for realizing topological superconductivity and to observe Majorana bound states. So indeed, we have achieved superconductivity in these tin telluride nanostructures by doping them with indium. And you can see the onset of superconductivity in these various structures. But the key question here is actually, how does the structural transition affect this superconductivity and eventually affect the topological superconductivity? So what do I mean? These tin telluride is known to go through a structural transition from cubic to distorted cubic. And you can pick up this structural transformation in your resistance measurements because your resistance, as you cool your material, will have a kink. Okay, so this kink right here indicates the structural transformation happened, and then this lowers the structure in a lower temperature, the symmetry lowering structure is also associated with ferroelectric domains or ferroelectricity. So the key question is, how is the ferroelectric domains or the structures depend on the nanoscale dimension? So we actually then cooled our nanorods inside TEM directly to observe the phase transformation. So here is the tin telluride nanorod at room temperature. You see at this mag, there's not much to look at. When we cool it down, and this is now same nanorod, but at 12 Kelvin, we start seeing these dark bands that develop. And these dark bands are not due to diffraction contrast. If it were due to diffraction contrast, as we tilt the rods or swing the beam, we should see that these bands, position of the bands should change, but they do not do that. When we take a diffraction pattern, so this is a room temperature diffraction pattern. It's a cubic structure as we expect. At low temperature, what we see is that these single spots split into two. So here is that red box zoomed in, and you can see that the single spot split to two. So and then there's a little bit of a distortion. So what that means is that the cubic structure at room temperature got distorted, and then there are two domains, predominant domains. Here is the movie. We're now gradually warming up that rod. Oh, is my time up? So, and then as we are warming up, these dark bands will all disappear at 80 Kelvin. So at 80 Kelvin, all of the dark bands disappear. The intensity variations of the nanorod change pretty drastically. So we know that the structural transition temperature for this rod is 80 Kelvin. So this is the first direct observation of the structural transition of a topological nanowire. And you see that currently what we want to do is to look at atomic resolution, the domain structures. So I showed an example of electrical biasing for in situ TM, heating, and also cryogenic cooling to study phase transformations of various nanoscale systems and the nanoscale effects that you would uncover, which can help us understand the crystallization better and also understand how the electronic properties depend on these phase transformations. Just a couple of slides. Right now, I'm focusing on actually putting a electrochemical device inside the TM in order to study phase transformations due to lithium intercalation in 2D materials. So we have a number of studies that are coming out, which, if you're interested, can be found in the group webpage. So to conclude, one of my favorite approaches to study phase transformations at the nanoscale is in situ TM, because this gives us real space information. So it gives us how the heterogeneity at the nanoscale can affect the dynamics of phase transformations. And not only these things happen for traditional materials or at room temperature, but they also have implications for condensed matter phases. And our current interest is in topological materials. So to conclude, of course, it's the postdocs and grad students in my group that have done all the work. Many of them have gone on to start their own lab. At Yale, the sample for metallic glasses was provided by Jan Schurer's group. I didn't speak much, but Corey Warhan did a lot of MD simulations to explain our data. The phase change memory work was in collaboration with IBM, with Matt Brightsky and Wang-Ki Kim. And some of the topological materials, although I didn't show it, we have some nice Josephson junction measurement work that's in collaboration with University of Maryland and MIT. And some of the high resolution in situ work and cryogenic TEM work was done at Brookhaven National Lab, which is about 3.5 hours away from Yale, working with Ime Zhu and Myunggun Han and Ho-Lin Sin, who's now at UC Irvine. So with that, thank you very much. And if there are any questions, I'm happy to take some questions.
Yeah. Thank you, Dr. Judy. It was a very nice presentation, actually, which covers both phase transformation of in situ studies and also the topological insulators. I have some questions. May I ask, if you don't mind?
Sure, go ahead.
Yeah. Actually, I worked in the same kind of a system like PBTA, C2, ZRT5, and everything. So, what actually made you to choose this SNTE? Because we usually concentrate more on semi-Dirac and Dirac materials, main semi-metals and everything in order to find these Majorana particles, but we never think about this SNTE. And
so what made me choose this? I mean, the answer is rather simple. So I was at Stanford as a postdoc, and I worked on bismuth selenide, bismuth telluride, one of the early ones. And then I started Yale as an assistant professor. So I want to start something new. And then at that time, when I started, tin telluride just came out. So before that, we just think that topological insulators, time reversal symmetry is the only thing. And tin telluride comes out as a topological crystalline insulator, another class of topological materials. So it just so happens that it was the timing of when I started. And actually, this so my group has been working on tin telluride for the last 7 years. It's a little bit hard, but we continue because I think the promise is there. But there's a new compound I started to study, actually topological metal. I study quite a bit of topological metal, and the one that is my favorite right now is molybdenum phosphide, MOP. And we have exciting results in that regard, actually, which I'm gonna zip for now. Maybe in a couple of years, I'll see where it goes. Basically, it's a very highly conductive material, molyphosphide. And even at the nanoscale, the conductivity does not suffer as much. So that's pretty exciting. And we're trying to understand what the topological protection is to explain that.
One more question, of course, it's about more technical. For example, if you are facing the TC value is less than 7 or 4 Kelvin, do you have any how the pressure is going to help you to reveal the superconductivity of the materials? The pressure along with the temperature, you are just going down to 7 Kelvin, right?
Yeah, so using in situ TM, we're not going to be able to, so with in situ TM, we're not going to be able to study the nature of topological superconductivity. So that's with collaboration with Jimmy Williams at Maryland, who does the Josephson junction measurements. And his results are at 30 millikelvin. So there is a gap in the temperature range that we can cover. I think currently the state-of-the-art in situ TM can get down to about 10 Kelvin using liquid helium cooling.
Okay. Thank you. It was a very mind-provoking talk and the answering of the part. Thank you so much.
You're welcome. Shall I answer the questions? There are 2 questions. How to avoid contamination in microorganisms in TEM, especially from bacteria. So actually, TEMs that material scientists use and TEMs that biologists use tend to be different TEMs. So for TMs, for materials scientists, I don't think that I worry too much about contamination from microorganisms. I do worry about contamination from hydrocarbons or any other, say, dirt, for lack of a better word. And usually what you do is, it's either the samples are dirty or your TM is dirty. So if the TM is dirty, then you need to bake your TM, bake out the column for a couple of days, bake out all the contaminants. For your samples, often we do cleaning, plasma cleaning. So you blast it with a plasma to clean away or burn away a lot of contaminants. Yeah.
Okay. Yeah. So thank you, Dr. Judy, for nice presentation. And
can I ask one quick question? Hello?
Yeah, yes, sir. Please.
Yeah, it's very interesting presentation. Madam, just in case of your platinum, copper, nickel, like TEM interpretation is a single crystalline material. How do you index it for all the, for example, HKL, including all the phases? So just
you mean that's the metallic glass?
Yeah, like platinum, copper, nickel, phosphorus composition. So it's a single crystalline material. So suppose,
you know what, we did not really do a careful indexing. Actually, for this paper, all we said was that we observed single crystalline state and that it looks more like the P2 phosphorus platinum 2,5 structure, but we did not verify it. And then this is just based on looking at the diffraction. So if you want to do it, what you need to do is to tilt your nanorods in at least 3 different crystallographic orientations and get the diffraction pattern. But these are, about 30 to 40 nanometer wide rods. So it is kind of difficult to tilt it in the right orientation. So we just have this single diffraction pattern, and we just think that it's similar like this structure, but we don't actually know the phase, the crystalline phase.
Okay. In fact, I got this type of metal cluster compound with a similar type of pattern. So I would like to curiosity for indexing, just I requested. Okay. And maybe you might have seen that you are working with some battery, also lithium battery by the Institute TEM. So what is your experience, especially suppose?
Oh, okay. So I did a lot of preparation work. So I like doing studies where I can make a single device and then study these. So I'm making a basically field effect transistor on a moly sulfide, for example, and then running the lithium intercalation. So the last 3 years, I spent looking at lithium intercalations as a function of the thickness of the 2D materials, as well as heterostructures, and then looked at the dynamics of intercalation with Raman to study the structural phase and also electrical measurements by measuring the resistance, and all in preparation work so that for TM, in situ TM, so that by the time I do in situ TM, I know pretty much what to expect. And we've uncovered a lot of interesting things in it. So we're right now publishing them. There's a technical challenge of trying to do in situ TM. So right now, with all of our work, just liquid electrolyte or polymer electrolyte works fine. But for in situ TM, I don't want to do liquid TM. There are a lot of people that do liquid TM, but that's just not my taste. So I want to have a pristine area to look at. So that means that I need to use either solid electrolyte or polymer electrolyte well away from the region of interest that I'm looking at. And currently, we're trying to find out the right polymer electrolyte that will let us do that.
Okay. Anyway, thank you very much for your nice, interesting talk. Okay. Thank you, madam. Thank you. Thank you.
So once again, on behalf of VAT, thank you, Dr. Judy, for this nice presentation. Thank you very much.
Okay. Thank you. And thank you again for invitation.
Yeah, my pleasure. So we'll continue the session with Dr. Saikat. I hope the speaker has joined. Yeah. Hi, Dr. Saikat. This is Nirmala here. Yeah.
Hi, good evening. I sneaked into the last talk by Judy. It was extremely interesting. So anyway, let's start. I hope everything is going well with
it's
the
fine.
conference. Yeah?
Yeah, yes, Dr. Saikat. Yeah, it's perfect.
Okay,
So,
fantastic.
yeah, we'll get started. So, Dr.
So
Anand, yes,
go ahead.
please, Doctor. Yeah, yes, please.
So how much time do I have?
30 minutes.
30? Okay, don't worry. I am,
Okay.
Indians, they speak very fast, right? So I can go through the whole 3-hour talk in 30 minutes. Anyway, so.
Thanks for the understanding. So we'll get started. Sure. Yeah, so thank you once again for accepting our invitation. And it's a pleasure to have you here at the event.
It's my honor. It's my honor.
Our pleasure too. So for your session, we have Dr. Anand, who will be your session chair, introducing you to the participants. And followed by that, we'll have your presentation. So over to Dr. Anand quickly.
Is it audible?
Yes, Anand. Yes, please.
Yes, thank you. Very good morning, Dr. Saikat Talapatra.
Thank you. Good evening to all of you.
Thanks, you. We are very much delighted to have you as eminent technical speaker in the field of nanotechnology. He received his Bachelor of Science in Physics and Bachelor of Education from Regional College of Education, Bhubaneswar. Thereafter, he finished his Master of Science in Physics from Jadavpur University, Kolkata, and his MS as well as PhD from Southern Illinois University, Carbondale, United States of America. After spending some time at Rensselaer Nanotechnology Center, New York, as a postdoctoral research associate with Professor P.M. Ajayan's group. After that, he returned to Southern Illinois University, Carbondale, as a faculty. He is currently the chair and professor of physics at Southern Illinois University, Carbondale. His current research interest involves exploring and discovering nanotechnology-based solutions and applications in electronics, energy, and environment. Today, his presentation title on nanoscale materials and structures, a perspective on future applications in energy, environment, and electronics. Once again, we welcome you, Dr. Saikat Talapatra.
Thank you so much for such a detailed introduction. Let's start the talk because I think it's already getting kind of late there. So let me see how this goes. Okay. So can you guys see my screen?
Yes.
Okay, let us see if I go to presentation mode, what is going on there. Yeah, so, okay, I'll do the swap. So you can just see my screen, right?
Perfect.
Yeah?
Yes, sir.
Okay,
Yes, sir.
All right. Thank you, everyone. I know it's a very challenging time during the pandemic, and Professor Grace has really done a great job. I am a person who is really laid back, but she kept, okay, send this, send that, we are doing this. So thank you for keeping up with the schedule. So let me first start with the acknowledgement slide. Typically, I want to do it up front. I would really like to acknowledge all my group members as well as my collaborators. Let me bring this digital pen. So you can see that our group, very soon you will see that our group actually is extremely open for different kinds of collaborations. We get into mechanical engineering related research. Of course, physics related research is there, and it's, unless we collaborate, it's very difficult to make any progress, real progress in science. So today what I'm going to do is I'll talk about certain nanomaterials. Of course, I won't be able to cover everything that we do in our lab, but I'll try to show some of the very interesting phenomena that we have seen in past several years related to carbon nanotubes, some 2D materials. Of course, people are looking into 2D materials with a great deal, and then some energy storage materials, and how can we drive the field of nanotechnology in order to get new applications. There are a couple of ideas that we will go through. Specifically, today I'm going to talk about collaborations with, of course, Ajahn. He has been a great colleague and mentor. Some stuff that we are doing with Mauricio's group at Penn State, and as well as Singmao and Mesfin in environment, water purification, and so on and so forth, as well as some of the stuff that we are doing with our colleagues here at SIU Physics. I am extremely grateful and lucky to have a bunch of my graduate student colleagues, postdocs, who have worked day and night for last 13 years to make our lab, extremely productive. And of course, it's good to have a lot of people involved, because personally I am extremely lazy, so I just subcontract pretty much everything on them. So another important aspect is funding. I am extremely thankful to all these agencies who have believed in our ideas, who have looked at critically in our results, but ultimately they kept our lab going. So I thank all of these agencies, specifically National Science Foundation in the US Army Research Office, as well as DOE. Also, in the past several years, I have been lucky to collaborate with folks in IISER Trivandrum, SECRI, and ISC Bangalore, with Professor Vijay Mohan Pillai's group, as well as Shai Jumon's group in India, and part of some of the 2D material light matter interaction that we will talk about comes out of those kind of collaborations. Okay, so this is the overview of the research. I will quickly go over our research thrust, simple basic ideas. I'm hoping that there are a lot of students, and then we will go over several important topics that we are pursuing. So in a nutshell, what we do is, of course, we grow a lot of materials. Recently, we have been working on 2D materials, and then there are lots of applications, mostly in optoelectronics, energy storage, energy conversion, so on and so forth. And the material, there is lots of materials that we look into, we grow, we collaborate with different types of groups in order to get extremely inquisitive, nice, new materials. I will not be able to talk about all the materials, but mostly I'll cover some of the carbon nanotubes, some 2D materials, as well as applications in maybe catalysis, electrochemical storage. In the electronics, we will just look into field effect transistors, field effect photodetectors, and so on and so forth. Now, scale of things. I mean, this is very interesting that what we are looking at in case of nanomaterials is right here, right? So, and of course, this is a very old slide, but if you look at man-made things, that human capability today has gone to a point, I mean, that you can arrange specifically each atom, okay, of a particular element the way you want, right? So again, this is, I mean, of course, with this kind of innovations, you can only propel this field even better. Now, what does this do to a material? When you have a bulk material, you start with a bulk material and you start breaking it down, one of the key properties that it brings in is basically your surface to volume ratio. And this is a very simple routine you can do, that if you have a cube which has 4 unit side, if you just break it up into small cubes, what you are doing is you are exposing the surface area that is available, that is hidden inside the bulk. And so you can see here that your surface to volume ratio increases. So what that means, and this is true for any nanomaterial, that's the beauty about nanomaterials, right? I mean, you can increase the specific surface area. Okay, so that means what you are doing is you are actually doing more or getting more with less. So let us say you have a cluster. I'm sorry about this image, but I'll tell you, you have 147 atoms cluster, 93 of those will be on surface. If you reduce the size further, let us say you have 55 atoms, 42 will be on the surface. And if you have 13 cluster of atoms, 12 will be on the surface. So what it means is basically you are increasing the number of specific surface area available. It's true for every material. You start breaking it down, this is what's going to happen, okay? And that is why people are so much interested in looking into nanoscale materials. Again, then there are a whole bunch of other things, like there are normal physics that breaks down, you go into quantum mechanical principles and things behave in a different way. But if you are from a layman's perspective, that's what happens, okay? So I will quickly go over some of the materials and structures that we synthesize here. Carbon nanotubes, people are doing graphene for a while now. But before graphene, the idea was, if you have a pure carbon material, which is basically one-dimensional, and if you have a graphene sheet and you roll it into a tube, and that became your carbon nanotube. It's between the fullerene and the graphene era carbon nanotubes, where even now they are extremely important materials for future application. So, we use several synthesis process. This is a technique of growing carbon nanotubes all aligned in one direction. And you can, because one of the main idea in our group is if we are making something, it has to have some application. Okay, so that's why bulk production becomes important criteria in whatever materials we are using. So we can produce aligned multi-wall nanotubes. We can grow it on metal surfaces, which is fantastic. I will show you why. You can grow it on a metal wire. You can basically make freestanding buggy papers, and you can also pattern those, okay? So there are huge applications using these materials. We also grow single wall nanotubes. Again, CVD process, chemical vapor deposition process. As the name suggests, what happens is if you roll a single graphene sheet into a tube, you have single wall nanotubes. Now, the single wall nanotubes, when you are growing in a process where you can grow it in bulk, what happens is because of the surface forces, they tend to bundle. So you can see this is the single wall nanotube film in a 3-inch Petri dish. And you can, the SEM images shows that they are entangled bundles. And you can see basically your whole bunch of, what happened to the pen? Okay, yeah, whole bunch of nanotubes bundling together. You need metal catalyst to grow nanotubes. And you can see that although the tubes are clean, you do have metal catalyst embedded in there. And of course, I'm not sure if you are able to see it or not. This TEM shows that it has a different kind of diameter distribution, which you can pick up from Raman as well. We also grow nanowires, variety of nanowires through different kinds of electrochemical techniques, in templated techniques, hydrothermal method of growing, and so on and so forth. I will not be presenting anything related to the nanowire, so let's move on. Then 2D materials, after the discovery of, or rather isolation of graphene, people started looking at van der Waals materials which are connected through different layered with weak forces. One particular method, again, it comes to large scale production. We have seen that if you use a liquid medium and sonicate it with high power, you can basically exfoliate any kind of liquid, any kind of 2D materials, and you can get the bulk behavior. So basically here you can see that these are MOS2 flakes, very, very small, but you have very few layers. I mean, 2 to 3 layers of MOS2 flakes. Now you can do that with any kind of van der Waals materials without too much of damage. These are boron nitride flakes, graphene, of course you can do graphene, tungsten disulfide. So there are a whole bunch of materials that you can do. So liquid phase materials, again, small dimension, high specific surface area, chemically active edges. Some materials are optically active, and so on and so forth. So of course, and then there is possibility of growing these materials in large scale. Layered double hydroxide, again, we have seen that it is sometimes you can have, through hydrothermal growth processes, you can have thin layer with different sorts of layered, zinc base, copper base, magnetic material base, layered double hydroxide. Again, I will not be presenting too much of this, so just skip. And then we move, we also produce CVD grown 2D layers, mostly few layers, and this is a SEM image of MOS2. Okay, now let's move on to the next topic, that is energy conversion. And I will show you something which was a surprise to us a few years ago. So basically, we utilized carbon nanotubes in a process which is known as Fischer-Tropsch process. Chemical engineers and many mechanical engineers, they can understand that it's a basically conversion of gases to liquid fuels when you are passing it over certain catalyst, okay? And again, the key idea was that carbon nanotubes have different, very high specific surface areas, and you can immediately see what I was talking about is that if you look here, like you have specific surface area of multi-wall nanotubes ranging anywhere from 30 to 250 meters square per gram. And as you are breaking it down, your surface area increases. To give a comparison, bulk graphite has a surface area of roughly 10 to 15 meters square per gram. Anyway, so initially what we thought that, okay, we have carbon and it has metal impurities. You can load catalysts. Typically in the Fischer-Tropsch process, what happens is iron is the primary catalyst, or cobalt, and this is how you initiate. It's basically carbon monoxide and hydrogen, mix of which is known as syngas. And it's basically when you are mining coal, you get this byproduct gas. So what to do with it, right? So if you have a nice catalyst which can absorb CO and have time to react with hydrogen, you can actually get long chain hydrocarbons. So basically we started with aligned multi-wall nanotubes. The idea was to load the materials with iron. So we loaded the material with iron, but what happened was when we were looking at the material without the iron, just pure as grown nanotubes, we saw that that particular material also gave a very interesting feature of different kinds of products at different temperatures. So this is actually, it was actually tunable. So you run the reaction at higher temperature, you can get selectivity of different kinds of liquid fuels. And not only that, you can change the pressure and you can see that the distribution changes. And of course, this is a collected liquid fuel from one of our experiments, and this is wax, which is settling down. So what theory predicts, this is collaboration with Penn State and Oak Ridge National Lab. What the theory predicts is that because you have the carbon nanotubes functionalized during growth with epoxy groups, that gives you enough time for CO to latch on and react with hydrogen, and when the long chain formation happens, it becomes heavy, so it breaks out. So this was the specific idea. Now the good thing was we also figured out how to grow the multi-wall nanotubes directly on industrially used monoliths, which they use for coating catalyst. Okay. So this is one image which shows you have multi-wall nanotubes coated in this simple monolith, and you can still see that it will give you certain amount of products, more than carbon number C5. Okay. Electrochemical energy storage, India has done a fantastic job in this particular fields. So over here, what we are trying to do is basically trying to see how we can improve the electrochemical double layer capacitor by a combination of the conductive material, the electrolyte, polymer electrolyte, ionic liquid, and you have to have a balanced right combination of several materials to have the energy storage, which is basically viable in different kinds of application, right? So this is the basic idea. Of course, it will happen, formation of a double layer. It will happen in any liquid metal interface. But the idea is if you can tune it properly, ultimately you have charge accumulation, which gives you this capacitance values. Now, initially what we have shown is that you can basically improve the supercapacitor behavior if you grow carbon nanotubes directly on metal surfaces. So we have shown that it is possible to grow these carbon nanotubes in some kind of refractory metals. This is the Inconel 600, which is super alloy, and you can grow nanotubes on them, and then the results were pretty good. So after that, in our group over the years, what we have done is with the carbon material, different kinds of carbon materials we have tried. Of course, this is what I showed. Then we also utilized functionalized graphene. The key idea is to basically look at the energy density, because power density of capacitors, supercapacitors are high anyway. So to compete with the batteries, you need to push the energy density. So, and then we also had, flexible electrodes dipped in all solid state uh, electrodes with ionic liquid and gel polymer balancing them. So basically we have seen that with a combination of different kinds of nanomaterials and such, you are able to increase the energy density. Now in the next step, and this is one of the collaborations we are having in a group with Finland, they have shown that actually, if we are looking at a future perspective, where if you look at the international roadmap for semiconductors, what they are now trying to say is that it is going to be very difficult to have material, for chips, which is going to go on and on, even if you reduce the size of the material, right? The Moore's law has already hit, and then you have, if you want to pack more chips, then it's becoming problematic and so on and so forth. So the idea is heterogeneous integration of multifunctional building blocks in one single chip. Now, to do that, I mean, if you want to power the chip, so basically this is a model, you can think of a thought experiment that, okay, you have a chip on which you have energy storage, you have piezoelectric sensors, so on and so forth, you have chemical sensors, and then it's wirelessly connected for data transmission and things like that. So these are maybe the future perspective that what we can look at, right? So the next thing I will quickly go over, again, the same thing, specific surface area is very high. We have shown, environmental applications. For example, there are certain chemicals which are over here in some region, for example, trichloroethylene, TCE, PCBs, they are extremely dangerous to human health. Now, typically what they do here is you have a contaminated water body, you just go and you put sand on top of it, okay? So sand in the bottom, so that it contains the contaminant there, all right? So the idea was, can we increase nanostructure, the surface of the sand, so that its efficiency increases? So basically what we did was, the idea was, okay, we take sand is some sort of SiO2. Let us see if we can grow carbon nanotubes directly on the sand and then utilize it for the remediation process. So it so happened that we were able to figure out certain conditions where you can see that, you can grow carbon nanotubes directly on sand. And you can see that from the facets of these sands, there are aligned carbon nanotubes growing. And when you do the different types of TCEs, okay, you will see that sand, which is coated with carbon nanotubes, had like several orders of magnitude higher absorption than just pristine sand, okay? And that one of the reasons is the chemical activity, activity of the carbon nanotubes. It's functionalized on the surface, is able to absorb more, okay? As well as the specific surface area. You just simply increase the specific surface area of the material. In the same way, recently we have shown that experimentally and then theoretically, it was also shown that why it happens, there are certain orientation of another, cruel contaminant, benzoic acid, that multi-wall carbon nanotubes, single wall carbon nanotubes are extremely good in removing contaminants. And this is some comparison with other carbon-based materials in here, but you can see that with single wall nanotubes, it's even more. Okay, so now last few minutes I will spend. So I have merged these two things because it's electronics. Some of the things are interconnected. So basically what I'm going to talk about is our recent few years ago, we started looking at 2D materials based electronics, not graphene. The geometry is mostly in the field effect geometry, where you have a source, a drain, and you have a backgate. Whenever I'm talking about simply field effect transistor, there is no light, but in the same architecture, when we are putting light, we can do the measurements related to photoconductivity and so on and so forth. Okay. Now, of course, graphene is there. It's a semi-metal, and people have figured out, you can actually, grow a whole bunch of layered materials. 500 is less. I mean, now people are saying you can get to 1500 or more, because this reference is several years. Now you can see it spans everything. You have electronically, whatever you have, 2D materials span everything. And in fact, people have shown that you can just make a FET based on 2D materials. So obviously they are flexible. You can print it if you want. So it's very interesting field it has become. Okay. So now, and people have also shown magnets. Good thing about this is you can really tailor the properties of these materials, okay? Because these are layered materials. So as you are decreasing or increasing the layer, their electronic property completely changes. Here I will just show one of our recent work with indium selenide. So you can see if you keep reducing the thickness of the indium selenide field effect transistor channel from roughly 20 to 100 nanometers, the field effect mobility decreases. Okay. Similarly, I mean, these are other parameters that you can figure out what is the mechanism of charge transport and so on and so forth. If people are interested, we can talk about that more. Now, again, interesting phenomena. We have seen metal insulator transition in 2D van der Waals layer of copper indium selenide. We have a basic idea of why it is happening. But more importantly, our 2D materials is interesting because different materials come with different band gaps, optical band gaps, electronic band gap. Okay. Now, what that means is that you can activate these materials by exciting with different kinds of wavelengths, okay? And so that means they are a very good candidate for making photodetectors or photo switches. I mean, people have looked at so many different materials. It has huge applications in, of course, IR detectors, imaging, remote sensing, you talk about it. So I will quickly summarize. We have worked on with collaborations with different materials. We have looked at MOS2. We have looked at heterostructures of MOS2 and boron nitride. We have looked at selenium-based 2D materials, ternary alloys. And so basically, you can see that if you have indium selenide-based material, you can see that as you are pushing laser power, the current in a field effect transistor keeps on increasing. And this is an on-off cycle, which tells you that the moment you turn the laser on, current goes up. And you can see that if you increase the gate voltage, your responsivity, which is a basic parameter of any kind of photodetector, also increases by 2-3 orders of magnitude. Similarly, we have done P-type WSE2. This is a collaboration with Florida National High Mag Lab and Jackson State. So again, here you can see that at high gate voltages, you have several orders of magnitude higher current. Now, if you look at any kind of photo gain material, the idea is you have to have very high responsivity as well as fast response time. People have looked into many materials. Okay, so now what happens is these are the materials that we have done in our lab. And if you look at, I mean, of course, these are exfoliated, very defective. So that's why they're slow. And then you have different kinds of materials. Let me quickly go back because, yeah. So this is basically all the materials you can see. If you have high responsivity, it is tricky to get response times very fast. Okay. Now, what we have tried is we have looked at a copper indium selenide, very nice material. And it has, as you can see, the currents are pretty high in a small device, 10 micron device like this. And not only that, you can see that some of these devices, the fall time, the switch off time is in micron orders, as well as the detectivities are higher than commercially available silicon photodetector, which is on roughly 10 to the power 11 or so on and so forth. And it has a broad brand response, right? So now if I go back to the chart, so you can see that copper indium selenide, at least what we have seen is a little bit ahead of the game. But you know, new novel materials are needed to figure out how to get to a fast and high gain material. Okay, so now I will quickly go over, you know, some of the work that has been done all over the world, and some concepts like maybe a good way is to create van der Waals heterostructures for broadband photodetectivity and so on and so forth. People have started looking into creating new artificial 2D materials by stacking, layering, similarly doing a PN junction and so on and so forth. Multiple functionalization of 2D materials and so on and so forth. And also there is some, I mean, this is the latest work that we are working with in collaboration with Jackson State and Florida State. There are certain materials which are anisotropic electrically. So will we have some kind of functionality out of a single material which has two different properties in two different directions, so that you can utilize it as an on-off switch in the same, you know, or a Boolean logic as 0-1 in a particular direction. So these are some of the ideas that we are looking into. So with that, I will like to thank all of you for your time. And like I said, you know, I can finish it in half an hour. So if you have any questions, please feel free to answer. I mean, feel free to ask, and I'll try to answer as honestly as I can.
Very informative lecture by the Professor Srikanth. Sir, I have the one question, the very basic question, and two more questions from the participants also. The first question, my basic question, what about the thermomechanical stability of MWCND grown on the flexible substrate, maybe the PET substrate?
So you mean if we are heating it up, how it
Yes, sir, exactly, sir. Yes, sir.
So we haven't specifically looked at the heating behavior when we are growing the the nanotubes on flexible substrate, the flexible substrate that you have seen. However, in one of our current investigation, what we have seen is if you grow it directly on very thin metal foils, that's an ongoing work. And then if you flex it and heat it at the same time, what we have seen is it doesn't destroy the electrode in any way, as well as it shows typical behavior of capacitance increasing when you are heating the whole device. So basically we have seen it in room temperature conditions up to 80 degrees centigrade, but those nanotubes were grown directly on metal. With the flexible ones, we haven't done thermal property checking of the capacitor devices. That's a very good question, because industrial application happens, within a range of temperature, right? Does that answer your question?
Yes, sir. Yes, sir. Thank you. Sir, the 3 questions from the participants. The first question
Absolutely.
from, yes, sir. First question from Mr. Agash Srivastava. Yes, sir. Is it possible to make a large area molybdenum disulfide and graphene heterostructure on nano-thick metal layer?
Large area meaning how large we are talking about?
Is not sure about large areas given. Maybe in terms of large area electronics or something, sir, towards the display applications. Okay. Yes,
Yeah,
sir. One more as a continuation.
It's approximately 2.5 centimeter to 2.5 centimeters, sir. The question is.
Okay. Yeah, I think people have already shown that using CVD, you can actually grow large area, wafer scale. 3-inch wafer, I'm forgetting the name of the group, but few groups in Korea, South Korea, they have shown that you can do wafer scale fabrication of graphene. And there are other groups which have done heterostructures, MBE, the molecular beam epitaxy. Penn State has a big 2D crystal consortium. I think if you want to check out, you can ask them for samples, because the idea of the 2DCC is that they can make samples and send it to you. You guys can check the 2D crystal consortium. So with MBE, one of my students just visited, so he was able to grow, it's the MBE process. So you can grow any kind of layer heterostructure. You want graphene, you want MOS2, you want indium selenide, bismuth selenide, you just name it, you can just grow large scale. So yes, you can grow it. With CVD, it's challenging. It depends on how good your conditions are. But there are, even in our lab, when we were trying to grow MOS2, I showed small triangles initially when we were trying to set the parameters of the CVD, playing with pressure and everything. We saw that we were able to grow thin, completely covered films, but they were contaminated with oxygen. So it was MOS2, some form of O3. So that's why we never actually got, maybe it had good catalytic property, who knows. So yes, it's possible. Yeah.
Yes, sir. Second question from Dr. Preetham Paradwaj. Which metal combination can bring novelty in structure of layered double hydroxide to increase its absorption efficiency for dyes in water purification treatment?
Okay, so that's a very interesting question, because you see, we have tried to grow the layered double hydroxide material, but it by hydrothermal or chemical bath deposition. Now, the idea is it's very difficult to control the layer thickness, because if you just change the temperature, I had a very good student who graduated and left for a faculty position. So he was able to control it to the, very thin layer. But for water purification, I am not sure because there are many folks, depending on what contaminant you are planning to remove, you can use infusing it with iron. Okay. That might help. Again, depends what you want to clean up, right? But again, it's very difficult to have iron dope like layer double hydroxide. We have tried, but it won't grow the way we want to. It will cluster or give you some cubes or something like that. So, but typically, again, like I said, depending on the type of contaminant you are planning to remove, it will depend on that. I think that would be my best guess.
So the one more question.
Mm-hmm.
Mr. Vadim A. Borisov, what is the newest materials used for LED?
Mm-hmm.
The continuation, whether Maxine is Maxines for production of LED can we use?
Okay, so now in the exploratory stuff, I think light emitting diodes, many people are looking at emitters with 2D materials. Again, selenide based, there are some. People are also looking at single photon emitters, for quantum information system. For that, typically they are using functionalized carbon nanotubes. I mean, if you really want to know what is the future of emitters, so both single photon emitters and detectors will be needed for quantum information, and specifically, light emitting diodes, you can depending on what you want, because the PL of some of the 2D materials are pretty good. Now Maxine, I mean, I saw that Yuri is giving a talk, Yuri Gogossi, and his lab is pushing the Maxine materials. I am not sure conductivity wise how good these Maxines will be or how easy it is to make a single flake Maxine device, because Maxine typically does not, I mean, that's my opinion. I mean, don't think that what I'm saying, everything is true. Maxine is not a van der Waals layer materials. Okay, it's a 2D material, but again, it depends on your definition of your 2D material. So Maxines are pretty good in other form of applications, but what I have seen so far, getting a field effect from Maxine is kind of tricky. Even if you get it, it does not compare that well with your inorganic semiconductors. Does that answer the question?
Okay. Yes, sir. So one more actually, Miss Deepika Ganguly. Sir, for growing CNT, will the number of layer depends on carbon-hydrogen bond continuation? Like mostly methane is used for scent and acetylene for MWCNT.
I mean, so you see, for growth of carbon nanotubes, all you need is the right temperature, a good catalyst, and any organic material which can give you the supply of carbon, right? Now, depending on, yes, the short answer to this question is yes. Depending on what kind of precursors you are using, you will either get single wall nanotube or you will get multi-wall nanotube. Now, there are different processes. We use ferrocene xylene process of aligned growth of multi-wall nanotube, because for some applications you need the growth to be aligned. And that helps us. The ferrocene xylene process is good because you do not need a metal deposition layer on the substrate. You can just bond a mixture of ferrocene and xylene, pass it through the CVD. You will have catalyst, iron catalyst coming from ferrocene. You will have carbon source breaking up from xylene, and you get aligned carbon nanotubes, which are multi-wall. You can do the methane acetylene process if you are planning to grow very thin wall carbon nanotubes. And the single wall nanotube we grow, it's a very high temperature process at about 1200 degrees centigrade, and we just bond ferrocene. So ferrocene is basically you have iron and then you have 4 carbon attached to it, right? So the idea that you are basically bonding that molecule and letting it regroup as a completely new material, right? So that process happens at a very high temperature. We do not use any precursor gas, just the flow gas of argon. You mix, we use little bit of sulfur, and there is a reason that you want to cap the catalyst so that you just get single wall nanotube majority of it. That's just ferrocene. You burn it at 1200, 1180 degrees centigrade, and what you get is a single wall carbon nanotubes. So depending on your process, yes, the number of layer will vary. That's what is well documented. But then again, you can, if you have, but basic idea is you need to have a catalyst, you need to have a carbon source and the right amount of heat. That's pretty much it. Okay, and that is in every chemical vapor deposition process, right?
Thank you, sir. For that, thank you, sir. Thanks for the detailed post presentation discussion. Thanks for.
Yeah, thank you, Anand.
No, it's my pleasure.
Thank you, Anand, for sharing. And once again, on behalf of BAT, thank you, Dr. Saikat, for this wonderful presentation. Thank you. Have a nice day.
Yeah, all of you have a great conference.
Thank you. Thank you so much. Yeah. So we can start with the next session. Dr. Kannan, good morning to you. I hope you join.
Morning.
Yeah, good morning. Hi, Dr. Kannan. How are you?
For you, right?
Yeah. Good. Thank you. So, yeah, without, I think we can get started. Dr. Raja Sellapan will introduce the speaker, Dr. Kannan. Yeah, over to you.
So, good morning, Dr. A.M. Kannan. So, it's my great pleasure to just introduce Dr. A.M. Kannan. So, Dr. A.M. Kannan currently is a full professor and graduate engineering program chair at the Polytechnic School, ERA, A. Fulton School of Engineering at Arizona State University. So, Dr. A.M. Kannan received his PhD from Indian Institute of Science, Bangalore in 1990 in the field of electrochemistry. So before joining Arizona State University, he just worked in some reputed organization, to just name a few. He just served as a scientist at SPIC Science Foundation, and he also was technical lead in Excite Batteries India Limited, and he was working as a chief scientist, Coke Scientific, United States of America. His current research includes lithium-ion batteries, fuel cell, photoelectrochemical water splitting. He has authored several research papers and has many patents to his credit. So currently he serves as an associate editor in the International Journal of Hydrogen Energy, and he is also the editor-in-chief research and reports in chemistry. So without further delay, I'd like to welcome Dr. A.M. Kannan to deliver his talk on enhancing interfacial charge transfer in tungsten oxide, bismuth vanadium oxide, photoanion heterojunction for photoelectrochemical water splitting. Thank you very much.
Thank you, Dr. Raja Sellapan. Thank you, Dr. Nirmala, for inviting me. So let me share. All right. Can you see the screen?
Yes, yes, sir.
Yes.
Okay. All right. So I think it has been probably a very long day for all of you. So I'm going to make it relatively shorter for talk on photoelectrochemical water splitting for production of hydrogen. So as we all know, I think most of the countries these days are planning to come up with a hydrogen economy roadmap, unless they have already one. So in fact, in India, the hydrogen roadmap was started probably about 10 years ago with Ratan Tata as the lead person, but I'm not sure where the hydrogen economy roadmap stands there, but I think the US, it's very, very strong right now. And the goal is to actually make multiple hydrogen fueling network to introduce hydrogen vehicles, including larger trucks. So when we talk about the hydrogen economy, it is by using hydrogen as an energy carrier for various applications, including whether it is a transportation application or a stationary or residential application, industrial and other commercial sectors. So we all know hydrogen is the simplest element known to human. And even though hydrogen is the most abundant element on the earth, unfortunately, it does not occur naturally as a separate gas. But, fortunately, it is always with water in combination of oxygen. But, once we separate the element of hydrogen from water, we could use the hydrogen for producing electricity by directly converting into electrochemical devices or by even burning as a fuel in internal combustion engines and other sources. In fact, many countries are also now thinking about directly using hydrogen as a heating gas, but I think there are many applications where you can also find the hydrogen in the mix of natural gas because the energy content of hydrogen gas is extremely high. So the reason why we harp on hydrogen is mainly because of the motivation we get from the relatively higher or the highest energy density based on the gravimetric value. As you see in this bar graph, the hydrogen actually gives you almost 3 times the energy density of gasoline, which has been the industry standard for many decades now, right? So 1350 watt-hour per kilogram for gasoline, whereas for hydrogen it is 39,000 watt-hour per kilogram. But for volumetric energy density, gasoline gives you 9,000 watt-hour per liter, but for hydrogen it's extremely low because of the lowest density of any gas known to us. So this is the major reason why we want to use hydrogen as an energy source for various applications. But when we look at the so-called hydrogen economy, it's not easy because hydrogen is not available freely, so we need to produce. So we can make hydrogen from various sources, but when we produce hydrogen, we don't have a distribution network and also storage capability right now, but technologies are in the verge of getting commercialized, whether you distribute by storing it in liquid form or solid form or in highly compressed form. And in terms of using hydrogen in various applications, we need to certainly make or use technologies available for converting them to produce electrical power. And the generated power can be used or actually is being used for many applications, including automobiles, smaller vehicles, and trains, and also various large-scale power generation systems with zero emissions. So in other words, whatever you see here are all the major difficulties or hurdles, but I think they open up lot of opportunities for research and development organizations, including universities. So when we look at decarbonization through hydrogen, hydrogen can be actually made as a gray hydrogen by decomposing or by reforming natural gas or from gasoline products, mostly from hydrocarbon-based products. But you can also make hydrogen as a blue hydrogen, where you can use the biomass as a feedstock. But the best hydrogen is listed as a green hydrogen, where you would want to use, renewable sources for producing hydrogen, including solar, wind, and other related technologies. But once that happens, the delivery and distribution is going to certainly happen through pipelines. So once you have pipelines with a longer distribution network, you can actually distribute or deliver hydrogen at the point of use for various applications, including, smaller vehicles with 80 kilowatt fuel cell system to, much larger systems, like maybe in megawatt level. So there are 3 megawatt units available in the market today for various applications. But apart from transportation applications, we can also use hydrogen for material synthesis or chemical synthesis, including steel making, and also for large scale applications, including thermal energy, as I said, for even kitchen, cooking application, also because of the extremely high thermal power from the hydrogen. But there are barriers which would certainly be handled by the various organizations, more non-profit organizations looking at the benefits from the zero carbon footprint technologies, and that would certainly going to happen. But the cost is again, one of the key factor these days in making the hydrogen applicable for daily use or most of the available technologies, including automotive applications. So right now we can actually drive the car, hydrogen fuel cell cars, to the hydrogen gas station and fill it for $13.99 per kilogram. So again, 1 kilogram of hydrogen is actually equated to 1 gallon of gasoline. So it's a GGE, gallon gasoline equivalent. So it is relatively easier to compare the pricing for the hydrogen with a gallon of gasoline. So there are roadmap. This is actually from the US. So as you see here, the plan by 2050 is highly ambitious, but by 2050, what we are going to see actually after about 10 years, we're going to have a centralized power generation system, and also using pure hydrogen, not by mixing it with natural gas for various heating applications and also in the manufacturing. But otherwise, as you see here, there are multiple plans in place to make the hydrogen as a centralized or distributed for smaller applications to large scale applications, including more transportation in terms of reducing the carbon footprint. So it's even predicted that by 2030, in about 10 years, there may be about 17 million tons of hydrogen, which is going to be used for automobiles and also for other vehicles, with more than 4,000 hydrogen filling stations across the nation. So right now in the whole world, we have about 600 hydrogen filling stations, out of which there are about 150 stations in the US right now. When we look at the hydrogen production technologies, it is important to classify based on the timelines, near term, mid-term, and also long term, but also in terms of the size, like a distributed and also centralized. And in the distributed size, you have a plant size of, say, about 1,500 kilogram per day production, and medium and large scale from 50,000 to 500,000 kilogram, per day plant capacity. But if you look at the technologies which are being looked at for hydrogen production, ranges from natural gas reformation, large scale, to coal gasification with carbon capture and storage, including electrolysis, high temperature electrolysis, solar thermal chemical hydrogen, photoelectrochemical water splitting to produce hydrogen, and also photobiological. And in the blue, it's a bioderived liquids or microbial biomass conversion. So there are opportunities in various areas, whether we are looking at really greener or blue hydrogen generation in the next decade or so. So again, as I mentioned, the cost has been one of the major factors in making the hydrogen commercially acceptable for various applications. So if you look at, also in terms of carbon footprint. So when we try to produce hydrogen, we should also look at how much carbon dioxide we generate. So if you look at when we say generate a kilogram of hydrogen, how much is the weight of carbon dioxide coming out? So it ranges from, photo fermentation, that's probably the lowest, less than half a kilogram carbon dioxide generation when we generate or when we produce 1 kilogram of hydrogen, all the way up to more than 10 kilogram of carbon dioxide if you use the steam methane reforming without carbon capturing and storage. So this is based on a plant with a 380 kilogram hydrogen production per day with a 90% capacity factor. If you use natural gas at $10 per million British thermal unit, that's a cost per unit. So that would actually hit, if we without carbon capture, it may go all the way down to $2 per kilogram. So in fact, the US Department of Energy has set a target of hydrogen pricing at $4 per kilogram dispensed, meaning hydrogen production cost plus distribution and generation, distribution, and also dispensing costs. So the target is like a $4 per kilogram hydrogen. And hydrogen still has a lot of advantages in terms of weight. So if you look at, say, this is just a diesel for just a comparison. So if you use a high pressure hydrogen to make the gravimetric energy density of hydrogen useful for various applications, specifically for automotive applications, in a typical car, we might need anywhere from 5 to 6 kilogram of hydrogen, which would give you 200 kilowatt hour, which is huge. Because for a typical normal sedan, for example, if you look at say Tesla's Model S, they use up to 100 kilowatt hour. So if you look at the weight of the battery, that's about 540 kilogram. Whereas if you look at the hydrogen weight, you only need 6 kilogram of hydrogen. So these are all the major, again, benefits with the hydrogen for automotive applications, whether it is for smaller vehicles or larger vehicles. So in the smaller vehicles, it is easier. There are automobiles from Toyota, Honda, and Hyundai, including small vehicles with 4 or 5 passenger size. And this is possible. They are available for outright purchase or even lease in the United States, and the things are going to take good shape in other countries. And if you look at the vehicles in terms of dimensions and also the battery or fuel cell or hydrogen-based fuel source, so it's a natural progression that the larger vehicles would be the first ones, or they have the advantage of accommodating fuel cell systems and also fuel at a higher pressure. So certainly, trucks are going to take a front seat in making use of the hydrogen technology for transportation. In that context, actually, there's a company started actually in Phoenix, Arizona, not far away from our campus. So they are in the manufacturing stage right now for large trucks for materials movement using hydrogen and fuel cell technology. So in other words, the hydrogen requirement is critical for making the fuel cell technology commercially viable. So when we look at hydrogen production, so this is exactly we are working on. So photoelectrochemical water splitting, because you can actually get hydrogen, solar to hydrogen efficiency of almost 10%. So that's pretty high for low energy input technology. So the important factors are the efficiencies, including absorption, bulk, and also surface, light harvesting, and charge separation, and also charge transport across the interface. So our goal in this brief study is mainly on improving the interfacial charge transport by reducing the resistance. So there are major criteria for a light absorber and also the challenges and opportunities. So challenges are mainly the material stability and corrosion, energy loss, and like any other device or any other material characteristics, that's always degradation with time. But based on what strategy we follow for improving light absorption or for improving the heterojunction to enhance interfacial charge transport, or what we exactly do for corrosion mitigation and all those things would lead to a practical level device with the commercial operations. So the electrode configuration, which we are going to see in a few seconds, it is based on the conducting glass and bismuth vanadium based materials. So as we all know, bismuth vanadium is a very attractive material, but it has a lot of difficulties. So we start actually with doping this material, and not just doping, and then we look at say heterojunction, and then with the heterojunction we try to improve interfacial characteristics. But in addition, we also try to come up with additional interfacial layer between the heterojunction layers. So if you look at this circle, there are multiple electrode fabrication techniques. If you start with metal organic decomposition, sol gel, spray pyrolysis, ultrasonic spray coating, dip coating, atomic layer deposition ALD, spin coating, spiral coating, hydrothermal electrode deposition methods, CVDs, and vacuum deposition. So, even though there are too many methods available or explored in the past, we actually took ultrasonic coating method for making the electrode. So as you see here, we start with F2O glass, and then put the tungsten oxide precursors, and then bismuth oxide. And we also actually have a dopant, which is a sulfur for doping into the bismuth oxide layer. And then we deposit the precursor for bismuth vanadium oxide, and finally we annihilate in air for a couple of hours at 500 degrees Celsius. So the material is a multifunctional layer with a thickness and the material in the nano size range, with very well controlled fabrication approach. So if you look at this scanning electron images, the one for bismuth vanadium oxide, so these were all made separately to look at the surface characteristics, not as a whole. So bismuth vanadium oxide, or tungsten oxide, or bismuth oxide, and this is the F2O layer thickness. So all these materials have a different particle size and shape, but almost all of them are almost homogeneous with a nano porous morphology. So these are very critical for materials utilization with a proper acid infusion or electrolyte infusion into the bulk of the electrode materials. This is the final electrode surface where we want to see the characteristics of the bismuth vanadium oxide, where, as I said, we have, so on the left you have the FTO and then tungsten oxide and bismuth doped, sulfur doped bismuth oxide, and it's a co-doped bismuth vanadium oxide, so co-doped with tungsten and gallium. So that's mainly for improving the light absorption characteristics or to expand the light absorption band. So you can also see the layer thickness here ranging from less than 200 nanometer, and bismuth vanadium oxide is about half a micron. And the EDAX showed the presence of various elements, and most of them are uniformly or homogeneously distributed. And you could actually also see the presence of sulfur, and the EDAX actually determines that the sulfur content is about 2.7 or 2.8 atomic weight percent within the layers. In order to check the absorbance and IPC, so we carried out light absorption experiments. So especially with sulfur doped bismuth vanadium oxide interfacial layer, that's an enhanced light absorption. So you can see here that goes to almost 84–85%. In fact, I don't have the data to show you on the interband formation, but when the sulfur gets doped into the bismuth oxide interfacial layer, we could actually see a presence of interband that actually helps causing the redshift or expansion of the light absorption band. And in terms of IPCE, as you can see here, the one in red, that's without the copy materials for the sulfur doped bismuth vanadium oxide materials. You can actually get IPC value all the way up to 60+%. And once we add copy surface catalyst, we can also have almost 70+% of IPC. So that's very important in terms of getting or expecting what will be the photoelectrochemical current density or photoelectrochemical performance. And the secondary y-axis in the chart on the right-hand side, you can also see the integrated or calculated current density, where we can actually expect all the way up to 5 milliampere per centimeter square. So crystal structure, so whatever we do, it's important that we make consistent materials whenever we make electrodes. So this is probably one of the first steps in ensuring that the materials form the required or expected crystal structure. So the bismuth vanadium oxide crystallizes in monoclinic scheelite crystal structure, and most of the doped materials are with additional heterojunction layers. There's no change in the crystal structure. So because the amount is not very high, there's not much phase change in the scheelite crystal structure. And in fact, in the XRD, we couldn't find any sulfur amount because these are all the patterns for the electrode, fabricated electrode on the glass substrate. So most likely there are not much sulfur present on the surface of the film, but with other methods we were able to identify the presence of sulfur. The light, this is a 1 cent or a 1.5 air mass solar simulator based, chop light based photoelectrochemical studies. So the experiments were actually carried out in potassium hydrogen phosphate, and we used sodium sulfite as a whole scavenger. So as you see here, we wanted to see systematically as how the performance enhances. If you look at the one at the bottom, this is intrinsic or pristine bismuth vanadium oxide that's at the bottom, and then It's a single doped, gallium doped bismuth vanadium oxide. And then the red one, that's tungsten, gallium, tungsten, and then co-doped, that is in green. So you can get closer to 2 milliamp per centimeter square for the co-doped bismuth vanadium oxide. But when we add tungsten oxide heterojunction, the performance jumps. So from 2, it becomes almost like a 3, close to 3. Then when we add bismuth vanadium oxide interface layer, it jumps further. You can see the blue. And then when we do this sulfur doping, it actually jumps further. So that becomes, I think, about 4 milliamp per centimeter square. And with the copper, it actually reaches almost 5 milliamp per centimeter square. And as you see here, with the sodium sulfite whole scavenger, you can actually get almost 4.5 milliamp per centimeter square. So what is important is also to look at the charge transfer characteristics, light absorption characteristics, and also charge separation. So, you know, depending on the whole absorption and depending on the charge separation characteristics, you can also calculate or estimate the charge carrier density. So we did, I mean, you know, a lot of fundamental aspects for understanding the materials features and how they perform in the photoelectrochemical cells. So for understanding further, we actually carried out the electrochemical impedance studies in dark. So that's at, you know, various potentials for various materials in the presence of or without whole scavengers. As you can see here, that's a one with sulfur doped bismuth vanadium oxide. You could actually see the lower impedance value for the one with the sulfur. And in fact, when you do a thorough analysis, so as you see here with the variation in open set, I mean, you know, electrode potentials. So you can see the total resistance extremely lower or the minimum for the one with the sulfur doped bismuth vanadium oxide. So these characteristics are very important, and we also developed based on the curve fitting. We also came up with a equivalent circuits to understand the bulk resistance and the series resistance, and also the capacitance value, surface capacitor, and also the bulk capacitance. So based on these Randall's circuits, so we can actually estimate the values. We did a thorough studies on how the resistance, you know, bulk resistance and surface resistance change for these materials when we polarize the electrode. So obviously the bulk and also the surface resistance is lowest for the sulfur doped materials. And when we look at the capacitance value, you know, as expected, the bulk capacitance is lower. And in fact, the charge the surface capacitance is the maximum. That's exactly we need for the Helmholtz layer. Then, you know, what is also important is the stability. So we only have data for 10 hours, but we plan to actually conduct for longer duration with more, you know, studies with the tandem cells. So you can see that the current density is higher, the maximum for the sulfur doped, co-doped materials or electrode layer. And we also have a setup for monitoring the gas generation. And you can see here the broken lines are the theoretical values based on the Faraday's law. But as you see, I mean, you know, the values are pretty high. And I will show you how our values compare with that in the literature. As you see here on the values for Faraday efficiency, the values are all the way up to almost 90% for hydrogen gas generation rate. So that's the Faraday efficiencies. So we wanted to see where we stand. So this star where you have this for the one with and without copper materials. So this PCD, so that's about 5 milliamp per centimeter square. So the materials are similar, or the studies are with almost identical approach for having an interfacial layer. And we also looked at the hydrogen production rate. So as we see here, based on the photochemical current density or photocurrent density, this is in line with the photocurrent density with the maximum hydrogen production rates. So based on what we did, I think the sulfur in the bismuth oxide interfacial layer helps actually, moving the holes to the surface, mainly to avoid recombination or to minimize the recombination, or basically by separating the charges. So that is mainly leading to the improvement in the photoelectrochemical water splitting performance. So obviously, photoanode is more important in the photoelectrochemical device. So the focus is again on the photoanode, but certainly, what our interest is in looking at the hydrogen production rate. So based on our calculations, we could actually exceed the 10% solar to hydrogen conversion efficiency. And the rate, if we normalize, we could get half a liter, more than half a liter hydrogen per minute per meter square electrode area. So the hydrogen obviously is one of the key energy vector in transforming our society into a sustainable one. So obviously with focus in various nanotechnology centers around the world. So materials play a crucial role in making the devices commercially viable with a longer duration and sustainable, because we can't look at materials which would ruin our atmosphere. So I have some numbers mainly on carbon dioxide emission based on the vehicle transportation, and you can see this is a picture of a power plant in the US. We don't want to continue with dirty power generation systems, right? So we want to make the systems sustainable, cleaner, with zero carbon footprint. I think I would stop here, and again, thank you very much for the organizers.
Thank you very much, Dr. A.M. Kannan, for your nice presentation on bismuth vanadium oxide based photoanode for solar water splitting. So indeed, it was a good talk. And I have a couple of questions.
Sure.
What is the active area of your photoanode that you used here?
So the active area is 1 centimeter square, but we are in the process of scaling up. So we, the lab based on the solar simulator, because solar simulator has a limitation of 1 square inch. So right now we have a smaller area, but in future we also want to actually test the cell with a larger area outdoor. So we don't want to limit the testing to the lab setup.
Okay. And you used this interface layer, sulfur-doped bismuth oxide. What is the mechanism actually? Because already there are a lot of work based on this tungsten oxide and bismuth vanadium oxide, which actually helps in separating charge carriers more efficiently. So what extra benefit this interface layer will? Is it a semiconductor?
We are actually in the process of studying with the XPS, bulk XPS. We don't have the results yet, but based on what we have seen right now is that during the heat treatment, the sulfur actually diffuses from the interface into both layers. And what happens is that the sulfur leads to the formation of interband. So the interband also reduces the band gap, right? So the band gap becomes smaller, that is in addition to improving or increasing the charge separation, it also enhances the charge absorption. So, or light absorption based on the change in the band gap.
And one more question regarding this hydrogen efficiency. You mentioned that more than 10% has been achieved actually.
Right.
And since the photocurrent that you showed is something close to 6 milliamps per square centimeter.
That's right.
With that, I think, can we achieve more than 10% efficiency? Because at least we need at least 8 to 9 milliamps per square centimeter.
That's right. That's right. So in fact, if you calculate, you may need more than 8 milliamp per centimeter square. These materials are, when we make electrodes, the goal is always to have surface catalyst. So we have not studied the surface catalyst yet. We have preliminary results with, I think it's an iron doped nickel oxide as a surface catalyst. The current density performance can be all the way up to close to 8.9 milliamp per centimeter square. So the study is ongoing. In fact, these are not published yet. So we are still waiting for the in-depth XPS analysis.
Some couple of questions also from the student side as well. And you showed that this bulk recombination, that after electrochemical impedance spectroscopy studies, you just plotted this resistance versus there is a plot actually that shows bulk recombination, and then
Yes.
This one, the second one on the right side.
Yeah.
So how to plot such kind of plot actually?
So when we conduct the impedance, so this is done in dark, and actually you need to monitor the impedance at a particular frequency. So this is with the various frequencies, right? But
Yes.
this is actually done at a particular frequency by scanning the voltage from lower to higher.
The right side diagram that you showed, this bulk recombination and electron extraction.
Yeah.
It is based
So
on
that's
this
at,
electrochemical.
that's at, I think, 1000 hertz of frequencies. So that's at a fixed frequency.
Okay. So have you used any binder actually?
There's no need for a binder. In fact, if I show you here. So when the electrode is fabricated, it is actually solution precursor. It is not that we make the materials and make a slurry and spray. It is precursor solution. And when we spray, you don't see the material. It's still transparent. And when we heat treat, you could see the color development. So there's no need for any kind of a binder. If you spray like a slurry, you need to have a binder.
And one more question that regarding this hydrogen and oxygen evaluation that studies. Normally, with respect to time, it's linearly increase but in your case, everything is something like 100% right from the beginning, the experimental values. On the right side.
Okay. So
why it is deviating from this theoretical to experimental? The dotted line, if I have seen correctly.
It may be possible that gas can also dissolve in the electrolyte, right?
Okay. Okay. So let me check.
We have one small quick question regarding Professor Kannan. Is very nice presentation. Just for curiosity, I'm asking: is there any effect of thickness? Sometimes your whole cell, what is the thickness of the cell? Is approximately the order of microns, or what is up?
That's a very, very good question, because electrode thickness makes a huge difference, right? So in terms of material utilization, in terms of having the minimum total resistance. So this is the optimum value. So we spent, I don't know how many months in terms of.
I understand. It's not so easy. Yeah, you have to play a lot of things. It's not so easy. Right. In overall, it's a very nice, interesting idea. So my one more quick question, according to your experience, this bismuth vanadate, or for example, the depth, how far while doing the illumination of light, how far 100% of material is participating, or is there any tricks, or just curiosity I'm asking, sometimes that once you illuminate your light, so you have a lot of three layers. How do you know that 100% has gone to depth? Just for curiosity, I asked you, or is there any way?
So the simplest thing is the IPC, right? Light absorption. Yeah. So if you see here, this is an indication, and based on these values, you estimate the current density, and this calculated current density can be compared with the observed or experimentally obtained current density to see how much is the most effective way of getting the light into. In fact, we were also thinking about in the tandem cell, the layers can still allow the unused light to be used on the other side of the electrode. So in other words, to your point, the light utilization or light absorption is into the depth of the or bulk of the electrode as well.
Okay, sir. Anyway, very nice presentation. Thank you very much. Thank you.
Thank you.
If there is no more question, I would like to thank Dr. A.M. Kannan for his nice presentation, and also on behalf of the organizing committee. So I'd like to thank him for accepting our invitation. So thank you very much, sir, and have a nice day.
Thank you very much, and good night for all of you. It's already 10 o'clock for you.
10 o'clock, yeah, here it's 10 o'clock.
Right. Yeah, okay.
So I'd like to thank all the participants for your active participants. So we hope to have some more interesting talk tomorrow as well. So I request all the participants to join at 8 a.m. tomorrow morning as per Indian time. Thank you very much, and have a good day and good night.
All right. Thank you very much.